So now coming to the last part of the instrumentation, right? So after completing with your instrumentation just before your detector, right? So we have made all the effort now to use whatever physics we had, knowledge we had, we have engineered it so that we can get the signal onto the detector. Starting from the source, we have now come to the detector. So now is that the end of the story? So what are the things that we need to, in fact we did air gap and scanning stills, all that just before it hits the detector. So now we need to talk about the instrumentation of what happens at the detector, and finally the output is going to be a image, right, that you are going to see. So what are the components that are involved after it hits the detector and how it comes out, that is what we are going to discuss now. Okay, so what we typically cover here is your film screen detectors. Film screen detectors, when I say, this is something that you already have seen. This is the same thing. You go after you have a suspected bone fracture, right? You would have gone, took an X-ray, and the radiologist will keep it in front of the white light, and right, you will see whether there is a fracture or not. So that's the film screen. So film screen detectors is what we'll talk about now, but we will have a separate module on digital detectors. Okay, so for now we will concentrate on the film screen. Okay, so here it is actually pretty straightforward. Now you should think, okay, if he is going to talk about just film screen, this is already there. How did Roentgen, make a first, or at least supposedly the first medical image, right? He was working, remember, he was working with Crookes tube, and then he was having film, photographic film, and then that got spoilt by a mysterious ray, and therefore he named it as X-ray. So the question is, fine, we already know that you have a photographic film, X-rays can spoil it, which is what Roentgen himself discovered, right? So that's it, we know that. So what is so specific about instrumentation for X-ray that we want to talk about, right? Yes, that did happen, but you know, the efficiency, it's only 1%, 1 to 2% of the X-rays that can be stopped by a photographic film. That means very poor, right? Now that we have already talked about terminologies to do with the exposure and other things, biosafety, we want to make sure that you have this conversion, right? When you want minimal X-ray, the energies that come out, you want whatever comes out should be used effectively, to be captured effectively. Otherwise, this is not acceptable from a safety point of view, right? So the question is, okay, this is good, but directly taking X-rays on a photographic film seems very inefficient. And then therefore, how all can we do, what all can we do to improve the efficiency, right? So in that regard, I mean, this is something that I always see, which is we are inherently lazy, right? So if I have solved a problem and you give me a new problem, what will I do? First I will see, oh, I have this solved already, I have everything, all the ecosystem ready, I know how to solve this. Now you are giving me new problem. My mind is going to think, okay, how can I convert the new problem into a problem for which I know how to solve, right? Right, I mean that's how engineering, it's about having knowledge, and then you have to be innovative in finding a way to solve the problem, right, or applying it to a domain. So here that's what we will do. We know all the photography film is evolved. In fact, now as we speak, it's all on the way out. How many of you go take a photo on a camera roll and then go give it for development? Very few, right? So that field of photography and photography film development evolved very nicely. So the idea is, okay, so instead of directly getting X-rays to photography film, can I since that part is very well established, can I find out ways where I can convert this X-ray to light, and maybe after it converts to light, I can capture it on a photographic film and develop it and so on and so forth, right? That's how you will think. It's a natural, at that point of time, if you place yourself, this is how human mind works. So that's what we will do. So they said, oh, we will have something called as intensifying screen. What is this intensifying screen try to do? The objective is simple. Objective is, on one side I have X-ray photons coming. Can I somehow convert this X-ray energy into maybe visible light, and then light photons can go spoil my photographic film, right? So that's what your intensifying screen did. So here what you see is just a cartoon or a sketch of a typical, we will complete this by showing. So when you go for chest X-ray, for example, there will be a cassette or a disc that is put in the detector, and they take the film out and they develop the film, and that's the film that the doctor sees in front of white light, right? So there is the X-ray film. So the film is this guy, right? The film is here. So film is here, but the film, before X-ray hit the film, we need something to convert X-rays to light, right? And therefore you have all these. So this is the outer casing. So there is a base material, and then there is a reflective layer. So the active layer in an intensifying screen is your phosphor here, and then some protective coating is here. So as you can see, you have film. So for example, your X-rays, right, should come from one side, right? It should come from the outside. It will come through this base. These are all supposed to be transparent, right? It shouldn't interact with the X-rays. It should pass, because that's coming outside the body, right? So it's coming outside the body. So these are all supposed to be transparent to the X-rays, but these are just providing you some mechanical sturdy. Film has to be, it cannot hang in air, right? So the intensifying screen is there to support. You have some base. After that, you have a reflective layer. What is reflective layer? We'll talk about it after we talk about this phosphor. This is the active guy. This is the active material in an intensifying screen. What is active? What is the role of the intensifying screen? Convert X-rays to light photons. That means this phosphor is a material that is going to take in X-ray energy and give out X-ray photons and give out photons in the light range. So this is the active material. So you have several, like luminescence, fluorescence. So we are talking about fluorescence here. So there are different types of luminance. Fluorescence gives you conversion. The light conversion is comparable to speed of light, right? 3 into 10 power 8. So this can convert, right? The light can be radiated, generated at a time constant that is comparable. Whereas you have phosphorescence, where it will take some time, after which it will give light. So the idea is, this takes energy from one range. So in our case, it is X-ray energy, and it creates light energy. So clearly, X-ray energy is higher than the light energy. So you are expecting that a few X-ray photons or few photons with X-ray energy which is coming can potentially, logic wise, can potentially produce more number of light photons, right? So this is your active material for that reason. So now the question is, what is this reflective layer? Oh, you create this light, right? This phosphor converts the X-ray to light. The light photons can go front and back, but you ideally want it to go spoil the film here. If it goes on the other side, you are wasting, right? Why should you waste? So you have a reflecting layer, so that if it goes there, it will again get reflected back. So clearly you want to capture all the light photons that are generated from the phosphor, which is converting the X-rays into the film here. Protective coating is just so that there is you don't damage the X-ray film itself. Okay. So the intensifying screen you understand the role of an intensifying screen. It is intensifying. What is it intensifying? Number of photons in X-ray, whatever is coming and hitting, but then number of light photons that come out is way more. And that light photon, when it comes, then you can use a photography film, because light photon, you know the efficiency of spoiling photography film and the whole ecosystem of photography film, what chemicals to be used, how do you develop it, all that is well established, right? At least the ecosystem is there. So, this is the solution. So, the idea is you have an intensifying screen and get the job done. Okay. So, phosphor convert the X-ray photons to light. So, what material? I mean, again, this is not something that happened recently. When Roentgen discovered this and photography work was going on, you may recall Edison, right? So, he was working, light bulb, right? So, he was working on several of these light kind of physics to do with that, and therefore materials. So, he was working with materials that can do this. So, he was working and he developed calcium tungstate as an alternative to do this conversion. Okay. And this is quite popularly used until recently, right, when your digital X-ray started to come and your rare earth metals, right, rare earth materials started gaining prominence. Calcium tungstate is one of the staple, that is the one that is mostly used, right. So, it is well characterized and it has been used for a long time and profitably so, and that is why it is withstood the test of time. Okay. So, convert, that is the active material. So, the idea is this: flash of light lasts only 1 into 10 power minus 10 seconds. So, you get this brief light. Okay. So, this is very useful also. You do not want the light to last for a long time. Then what is going to happen? The light is there going for a long time. That means it can spoil the film for a long time, right. So, natural disadvantages, you may have blurrings, you remember about the motion artifact and all those things. So, you may have temporal blurring because of that. So, you want it to be as quick as possible. Okay. So, so you want one of the desirabilities is you are going to exploit when the X-ray photons are converted to light photons, it has to flash out in time that is very short. What is short? 1 into 10 power minus 10 seconds, that is the order it takes, right. So, you want to catch this flash of light, or rather the film needs to be exposed to this flash of light. Okay. So, clearly you can understand, that means we are talking about similar principles. X-ray is interacting with the material. Now that our objective of the material is to do this interaction, that the output should be some characteristic radiations, right, characteristic photons that come out in light range. So, you have about 1000 light photons. So, it has to be dependent on, I mean, without even just by what we have covered so far, right, you should be able to guess what are the factors that going to determine this. Oh, there should be a energy, right, what energy is coming is going to have a role to play with the interaction, right. What interaction you want? You want the interaction such that the X-ray photons that are coming has to be absorbed by the material, and then it has to transition, give out light photons. In fact, you want one photon to give many light photons, one X-ray photon to give many light photons. So, what are the conditions? So, it will depend on the energy of the X-ray photon, it will depend on the material property, right, of this, how can it absorb, that is one thing. Then its conversion efficiency, how efficient is it to convert this energy into the photon energy, right. So, all these are factors. In fact, you will hear the term called as speed of screen, right, speed of screen. You might wonder, speed of screen, speed means typically we will think it is in that time, right. What is speed of screen? We will think, okay, what does speed got to do here, right? It will look oddball, but what it means is typically this conversion, right? I told about the material, energy level, its interaction, right, and its conversion, material's ability to convert one energy to give many photons. So, the speed of screen typically is used to refer to this conversion. Why? Because if I have high speed of screen, that means it takes small time, little time, because more number of photons are created, the conversion is high, then more number of light photons are generated. If more light photons are generated, the film can get exposed quickly. So, more the light photon, lesser the time to expose, right, the full film, right, the film that you are thing. And so, to spoil this film, you need only less time. So, speed of screen actually refers to the conversion efficiency of this material to converting X-ray energy to number of light photons, many number of light photons if it can produce. So, here typically you get about 1000 light photons per 50 kilo electric volt, when, right, that is the range when you operate your that is determined by your tube, X-ray tube, right, at that level. So, the energy comes out, this is typical. So, you are going to have variation depending on the energy level that is used, right. Again, this is from the X-ray tube, but then a spectra goes into the body, comes out, right. All of this is going to determine your light energy, light photons that are going to come and spoil the film. Okay. So, last but not so, radiographic films actually are nothing but, we are not going to talk too much about this, because as we just spoke about, it is just photographic film that is there. We have an intensifying screen and then that is used. So, there is nothing much that we will talk about radiographic films. So, what is radiographic cassettes? When you have this film, right, you saw the previous intensifying. So, all of this put together is your cassette. So, this cassette should be easy to open, you can slide the screen in. So, top part you will have one intensifying, bottom part you will have another intensifying, so that light, and you saw that reflective layer, right. So, that light goes in, it maximizes the chance of it interacting, spoil the film. So, naturally one side it has to allow the X-rays to go in, the other side you do not want the X-rays to come out of the cassette. So, on one side of the case it will be transparent to X-ray, the other side of the case basically they can have a lead coating or whatever, so that it does not exit the cassette. So, it is a typical cassette and the film will be taken out of this and developed separately. Okay. Of course, so it has all these mechanical design aspects, so that when you handle it you do not squish it and things like that. But otherwise it is a radio, this is something that is very common. In fact, it is very common in most centers for quick X-ray diagnosis, but here also mostly we are nowadays there is a rapid transition to digital X-ray, okay, that we will cover separately. Clear? So much for the instrumentation of it. We have gone systematically from source instrumentation to what all we can manipulate with the object, human beings, giving the contrast agent, right, that aspect, and then of course some instrumentation before the source and the object in the form of filters, restrictions, and then from the object to the detector again some sort of filtering and collimation, right, we talked about that, and then last about the detector system, which consists of a intensifying screen and a regular film. So, this is with respect to your projection radiography instrumentation. What we will see next is, from instrumentation we need to move to imaging, physics, instrumentation. So, now we will go to imaging, where we know the physics. Now, if these are the instrumentation, the output that you are getting, right, the image, how is it formed? Can we use the imaging equations that we derived or not derived? In the physics we said this is the fundamental law that governs. Using this instrumentation, have we been able to engineer it so that we can capture the object as a output image of a parameter? That is what we will do in the next lecture. Well, so we have covered the instrumentation aspect of projection radiography. So all the greens are things that we have covered. What we will now focus on is this image formation. Like we discussed, instrumentation, image formation and image quality. These are the three big modules we will cover in each of the modality. So before we jump into this, we will cover the physics of the modality. Okay. So with respect to X-ray, projection radiography, we will now start to deal with image formation. So here, unlike your we will use the same X-ray physics, right? So the subtle differences, subtle but very important differences come when we talk about image formation between X-ray based projection radiography and X-ray based CT, right, that we will cover subsequently. Why I say that is, here when we talk about image formation, in some sense you are not gathering the data and recomputing the image. What you get is, you have the film, right? What is recorded on the film is the image. Now the question is, when I say about image formation, how all we can manipulate the instrumentation so that whatever we are getting on the image as the output, right? How does this influence what we see on the output? That is what in projection radiography, because the film is formed, right? You just have to develop that and view it. So in some sense, what are the operations that you can, what are the parameters that you can control to form an image has to mostly to do with the instrumentation that we have covered so far and how we exploit it, rather than explicit reconstruction. Okay, that will come clear as we go along. So this is the paradigm that we are interested in. So when we talk about image formation, what you already know from physics is, oh okay, we are going to deal with a source, an object, right, a source, an object and a detector in the behind. Whatever you are capturing on the detector, now that we covered the instrumentation, the detector, if it is going to be your X-ray film, whatever you are going to capture on the X-ray film, the doctor is going to see that as an image in a light and make diagnosis, right? That is the through. So this is called as through transmission image. The output that you are using is a through transmission image, and the setup that you see here that we discussed even in instrumentation is a through transmission setup. That means you have a source on one side, detector on the other side of the object. So what we are going to deal now is, you might think, okay, what do I know about this? Right, when we talk about imaging from the physics point of view, we covered all the instrumentation now just recently. So from the physics point of view, what do we know about this image that we are talking about? What is the physics that governs? Oh, we talked about signal and noise, interaction of electromagnetic, right, with the tissue slab, remember. Then we talked about fundamental attenuation law, the photon law, right, exponential minus mu delta x, where x, that delta x we denoted for a thin slab, remember. So that means your image is formed if I give a source, right, n photons on the input side, the object is going to, what is going to come out of the object? It is going to be attenuated version. How much it is going to be attenuated? Oh, it is going to be attenuated by the law, photon law, e power minus mu delta x, right, depending on the material property and the thickness. That is what is going to come out. And we already talked about the instrumentation. Oh, if that comes and falls on the detector, there is a film conversion and photography is developed. So we know that. So what is new in imaging here? So the concept is same, the physics is same, right? But now what we need to do is, that law that we had, e power minus mu delta x, I equal to I naught e power minus mu delta x, right, exponential decay model. How are we going to account for? So that pretended whatever is falling on the material whatever came out of the material. That is the loss that we modeled. So, where all it is falling on the material, where all it is coming out of the material, that is when it is coming out, and what all goes and hits the detector, we need to put that in. That is why it is important, right. Otherwise it is easy, x photon n, remember we use this n and n naught, n minus n naught is equal to minus small n, that is proportional to your material mu and delta x. We covered this homogeneous slab, non-homogeneous slab, narrow beam, all that. Now is the real question, when you have a instrumentation, is it narrow beam? Okay, we will instrument that to narrow beam because that is the model we developed. Now the question is it actually hitting the delta x everywhere it is hitting? Is it hitting the same way, or because of the instrumentation something is not? You already have some answers, right. We already saw that the X-ray source is giving out diverging cone. So, we had filtration, we had restriction of field of view, right. So, because of divergence, right, and because of this setup, you have several factors that we need to incorporate in our imaging equation. That is what we will focus in this imaging module of projection radiography. This is the grand setup. So, you are going to see I have a source, I have a distance between source and the object, I am going to have distance between the source and the detector. So, the idea is I have an object plane, right. I have an object, the object is going to be collapsed to a plane. So, this is my object plane if you will, and this is my imaging, the film where the detector is, the detector plane. Okay. So, now we need to see what are the factors that are going to play from the instrumentation point of view, what are the factors and how are they going to get into the law that we, fundamental law that we wrote. So, we need to update the fundamental law, or we need to use the fundamental law for a given setup like this, which is what we will do now. Okay. So, in order to do that, just recall. So, this is something that we knew from before, your intensity at any point x comma y, right, we talked about this, right. So, it is the spectrum of energy that goes in. So, number of photons, n1 number of photon at energy level E1, n2 number of photon at energy level E2, so on and so forth, right. You have a spectrum. This is the rough sketch of spectrum that I was using, right. So, this spectrum goes into the body. So, these are all number of photons, this is the energy locations. So, Brahm straw lung, right. So, you have a host of different energies and you have different number of photons at each energy. This is going into the body, right, that is coming out of the X-ray tube. Now, intensity at x comma y, right, on at a location is whatever goes in, so S0 into that energy level, whatever goes in, exponential of minus, this is integrated over the path length r of x comma y of this mu, which is deliberately written as a function of x and y energy that it is dealing with, right. So, and ds is the your segment, so your path length that you are talking about. Okay. So, this is fine, this accounts for what we want to do, but this is too generic. So, we need to customize this to the setup that we have. That means, what is the path length, we need to be explicitly able to write. And is this all, is there any other effect that comes into modifying this equation because of the way the instrumentation is set up, that we need to be able to accommodate. Okay. So, that is what we will do now. Broadly, we will start with what we call as geometric effect. What do we mean by geometric effect? The effects that you see on the, so this is all to do with what you are going to see. What you are going to see is supposed to be an accurate version of the unknown underlying body, right? What you are going to see is your g of x comma y. What is the underlying unknown is f of x comma y. Remember back to our big picture systems diagram. G of x comma y should be as close as possible to your f of x comma y, right? That is our thing. So here what we are talking about is what are the effects. So you are having a system, you have some instrumentation that is capturing this f of x y or transforming this f of x y to g of x comma y. What we mean by geometric effect is because of the setup that is trying to capture, are we seeing any effect on g of x comma y? Not because of fundamental f of x comma y, but because of the geometries that are involved. So the output is different from the input due to the geometric reasons, right? That is what we want to categorize as geometric effect. So first and foremost, this is something that we probably used earlier also, right? Something called as inverse square law. That is, I have a source. What is going to happen to this source? Recall from the sketch that we have and previously, it seems like it is diverging, right? So when it is diverging, what do you expect to happen? Oh, at this point you have all of them concentrated. As it is diverging, right? As it is diverging, what is going to happen? As it move away from the source, oh, your intensity is going to drop. How is it going to drop? Oh, it is going to drop not linearly, non-linearly. How? Square, inverse square. So it is going to drop with the distance. The farther you move, remember we did this even when we talked about exposure and stuff, right? So farther you move from the source, because this is diverging that we are talking about, the intensities are going to fall off at square, inverse square law, okay. So if you have a beam intensity at the source to be denoted as IS, okay, you have a source, it is integrated as a small sphere. So whatever you have, sum total is your IS, and the intensity at the origin of the detector. Remember, you have this intensity, I don't even have the object, just the geometry that I am worried about. I have a source, I don't have the object, I have a detector. What should happen? What is there in the source should be at the object, right? I mean, should be at the detector, but it is not. Only at the center you have one value, and as you move away from center, because this is diverging, right? Depending on the distance, you can already see you have a center and it is changing from the center. So your I naught, if you call it as the intensity at the origin of the detector plane, right? Because this is diverging and the intensities are going to go down a square of the distance, what are you going to see, right? So if that is the case, then your I0 is IS by 4 pi d square. So what is this d? Oh, this is the distance between the source and the center of the detector. So at the center of the detector, you are going to have an intensity that is reduced. I have no object, so technically it should be IS, but it is not going to be. It is going to be reduced. How much? It is going to be reduced by 4 pi d square. That is the distance of separation between your source and the center of the detector. And this is very handy. This will be used again and again. Why? Because it is a very simple formulation, right? And it is very powerful. So just to complete our analysis, what is our analysis? Oh, we are not interested just at the center. We are interested, there is a detector plane, right? I have a detector plane. So what are the values that I will see in the detector plane? Clearly what you are saying is this is source, the source is diverging. So what will I see at different locations? At I naught, at the center, it is IS by 4 pi d square, because the distance of separation is there. So at other locations, what could it be? Same, measure the distance, right, of this point from the source. If this point, right, you have center of that plane, a distance to the center of the plane, and then you could use the d to calculate this diagonal, right. So let R be R of x comma y is a point in the plane of the detector. So, let that be the distance between X-ray origin and the detector point x comma y. You can clearly write your IR, whatever is there at IR, intensity R is nothing but source by 4 pi R square. When it is perpendicular distance to the center, that was defined as D, and therefore it is D square. If it is R, it is R square, right. So, this you can actually calculate. So, therefore, given the diagram, in fact the previous slide, the proposition, you see theta is the angle. So, you can have your cos theta. What is cos theta? Oh, I have the center source to the center of detector plane. So, that is my shortest distance, that is my D. So, this R is your hypotenuse. So, the angle included. So, cos theta is adjacent by hypotenuse. So, D by R, okay, straightforward. So, I have inverse square law that can be captured like this. So, I can tell at each point in the detector how much of intensity I will get, right. Fine, this is fine, but then if you substitute, what happens? IR is equal to, right, I naught. All I am doing is I am just incorporating it, making it more general, because I know my I naught, that is 4 IS by 4 pi D square. So, I am just writing my IR in terms of I naught using this cos theta. So, what is this saying? I mean, this mathematically it is straightforward, right, but just spend that extra few seconds to understand what this is saying. This form is easy, intuitive, or inverse square law that you would have convinced, but this mathematically straightforward, but it is very, what is it, what does this physically imply? That means this is saying on the receiver plane, right, on the detector plane, on the detector, even though I have a source, the source is sending diverging, right. What is it that you are capturing? You are capturing I naught. At the center there is one intensity value. As you move away from the center in any direction, right, you have a cos square variation in the intensity. So, you are going to see a cos square pattern, you are going to see a fluctuation, spatial fluctuation in terms of cos square theta, right, depending. So, the theta is basically, it is telling, you can look at it at the angle, the R, right. So, different locations in the plane. So, you are going to actually see a nice cosinusoidal or square of cosinusoidal variation. So, if you look at the image of the at the detector of a source that was a point source, you are going to actually see a fluctuation that is not homogeneous, that is going to have, this is without an object. So, now you see the problem. If I have an object and I see this fluctuation, will I interpret that as the object having a very patterned attenuation coefficient, or the object having a cosinusoidal shape? If mu is same, does it say the object is cosinusoidal, right, in 2-dimensional? The plane is not a plane, but it is having a cosine square variation, right. So, without, you see the complexity now, without even having the object, you are receiving something at the detector solely because of the geometry, where the source is sending out a diverging wave, and therefore, depending on the distances involved, the geometry is involved, you could actually see a pattern. In this case, it is a cosine square theta, right, nice pattern that you are going to see. So, this is something that we need to worry about, but more importantly, we need to update our equation to incorporate this or do whatever. So, why is this important? This inverse square law per se, just an example here, right. This is very common, commonly used, because it is a very common scenario. So, you have an acceptable chest X-ray, right, they have some setting, right, 30 milliampere second at peak voltage applied is 80 kilovolts, right. This is your X-ray tube configuration. So, now the person is standing at 1 meter. They are saying, oh, now you need to move the patient, you have to take the patient at 1.5 meter from the tube. but the settings is same, 80 kilovolts peak. That is what you want to apply. Question is, what is the MAS setting should be used to yield the same exposure, right? So the idea is you are asking the patient to move, in which case the exposure, right, it's going to change because it is dropping off with respect to D. What he is going to face, right, is drop off with respect to D. So if he is moving closer, you can reduce the exposure. If he is moving back, like away from the source, you have to increase because it is now diverged, right? So the question is, suppose it is now requested, if he is moving, what is the MAS setting to yield the same exposure? Okay, how do you approach this? Well, it's the same law that you need to use. Only thing you have to recognize is, I know this is at intensity, so I can have this as a old and new, right? So I can have my source. I had one source, so I will call this, say for example, source new and I source old. I know my D new, I know my D old is given, right? So if this is given, then what do I need to do? Well, I have to make one thing, make use of this fact, same exposure. So you can say, okay, it's all proportional, and therefore, right, it doesn't matter, I can do my I old, right, is nothing but your IS old by 4 pi D old square. Likewise, you can write it for new as well, right? IS new, I new, D new, we can do that. All I can say is, because I want to use the same exposure, I could say these could be proportional. So I can write IS new is equal to IS old times your D square new by D square old, right? That's all we need to do. So you substitute, you are given all the other aspects, you substitute and you will get some numerical value. What is more important is, of course, if you substitute, I will just you can punch in for the given values, you can punch in, you will see that it is coming out to some 67.5 milliampere second. Okay. So you notice why is this is important? You are using 30 milliampere second. Now you have to pump up to 67.5 milliampere second to keep the same exposure, because we know the image quality will depend on the exposure. So if I am keeping the exposure, if I ask him to move, it has all these repercussions. So I have to operate my X-ray tube to get out at 67.5 milliampere second. Okay, because he is moving back, if I have to have the same exposure, I have to generate more. So this is very so you cannot just say, okay, I was asked to take, can you move 2 feet back and repeat the experiment. If you meet 2 feet back, you have to change your X-ray setting. So all this is involved. Then the question is, you know, how much exposure, do we have to redo it? So it's because all this biological safety issue is there. So this is a very important routinely used formulation. Okay. Next is your geometric effect, is your obliquity. As in, what is oblique? As you can see here in the I have a detector. We were talking about detector being perpendicular, so that the source is coming and hitting, and the object plane and your detector plane are parallel to each other, right? That is what we were drawing in. But what if there is some angle, right? If it is not perfect, some angle, that is called as your obliquity. But when we talk about some angle, where is its effect? Oh, if it is going to have a theta tilt, what is going to happen? I have a center, center to center it is there. If it is slightly tilted like this, you can see from the cartoon here that if you have a center unit area, right, if that is the unit area at the center, if it is going towards the, because it is oblique, if it is going towards the end, that same area will be projected onto a larger area, right. So, it will be projected over to a larger area on the edge, because there is a obliquity. So, when it is perfectly perpendicular, no issues, whereas if it is going to have an angle, it is like your shadows, right. You will become, your shadow will grow tall or short depending on where the sun is, right. As it moves on, you might become taller and taller, your shadow will become taller and then you shorter. So, it is a similar thing. So, there is an angle that is involved. So, we calculate that based on, or incorporate that based on this unit area A that is marked, and we will say, okay, the effect, it increases the illuminated area in the detector. So, if there is small obliquity, then you have to understand that the detector is going to get hit in a larger area compared to what it would get hit without, when if it is perpendicular. Okay. So, if you have A to be the area orthogonal to the direction of X-ray projection, the projected area will be now on the detector is going to be A by cos theta. So, the idea now is we need to incorporate. So, one we already had distance, the other is with the detector. So, we can start to put it together. So, what we are interested is in our intensity. So, ID on the detector will be equal to I naught cos theta, right, because this cos theta area is coming in. So, your intensity is going to be varying with respect to cos theta. So, at the center you will have minimum, as you move away from the center you are going to have more distortion, right, that is what this is going to suggest. So, ID is I naught cos theta. Again, these are some things that you can do at the time of calibration. Okay. So, combining these two effects, one was cos square theta, the other was cos theta. So, combining these two, we get the variation to be I naught cos cube theta. Okay. So, just based on this geometry, we have not included any object so far, right, without even the object, just because of the distances involved, that is why it is called as geometric effects. The distances involved, you get this effect on the detector. You see that the intensity is not just whatever is just falling I naught, it's I naught is at the center, it is not I naught, it is not the same intensity throughout the detector plane, it is varying with a cos cube theta. So, quickly we will have a, okay, this is fine, is this how detrimental is this, right? Yeah, we understand there is a formulation, you have this effect in terms of cos cube theta. Is this detrimental or is it okay? How do we get a feel for the level of acceptance or tolerance for this, right? So, let us just do a example, right? Typical, your chest X-ray. So, you have your standard sizes, right, you are standing at 2 yards and using a 14 cross 17 inch X-ray, that is your field of view, right, in the detector. So, what is be the smallest ratio, this ID by I naught across the film, right. That means, you are saying that it is varying from the center, it is varying and in the form of cos cube theta. What is the maximum variation? That is what in some sense this is asked, right. What will be the smallest ratio, right. Smallest ratio means you will have the maximum variation that you can expect. So, what is your cos cube theta? First, if you can find this, that is what we want, right. So, what information do we have? Or we have the dimensions and d, distance. So, first identify what is the point where you have, which is the farthest point from the center. Oh, this is a rectangle. So, the farthest point is going to be along the diagonal, that corner. So, that is going to be square root of, right, you are going to have square root of 14 by 2 plus 17 by 2 is going to be 8.5 square, whatever that number is. This turns out to be about 11 inches. Okay. So, that is that point. So, what do you want? Oh, I want, what is my theta, cos theta? We had writing that, right. It was in terms of the r and d. What is d? D is given, that is your distance. So, you can write your r suffix d, right, which is this guy. You have that. What you need to do is your cos of theta, which we want to be the maximum. Say you have your d by square root of this guy, d square plus this rd square, d square plus rd square. So, you can get that, and if you substitute, you will get a value to be around 0.989, but that is cos theta. What we want is cos cube theta. So, that turns out to be about 966. So, cube of this is this. This is the ratio that is asked. So, about 3% variation, not a big deal, right. Well, it depends on, if this is the only contributor, then we will have to see how best we can reduce this 3%, or as we add on other effects, if there are more dominant guys, maybe we want to address that, and then this we will say, okay, in relation to that, this is just 3%. Okay.